All right, so I want to take the statics problem that we talked about at the very beginning of the semester and take it and use it as a vehicle in which we can talk about programming in VPython and representing our solutions graphically within that programming environment. So recall the problem we had was a ladder leaning up against a wall. The ladder has a length I call L, and it's at an angle theta. And there's someone standing on the ladder. The person standing on the ladder has weight W, and that person is a distance D up the ladder. So I'm giving you the L, the D, the theta, and the W, and what I want you to find is the force from the ground acting on the ladder. Now we're going to make a few assumptions. We're going to assume, for example, that the weight of the ladder itself is negligible. And we're going to assume that the wall here is slippery. If I put a friction force on that wall, I'm going to have a statically indeterminate problem, as we discovered that first day of class. So next thing we did was we drew the free body diagram of the ladder itself. Here's the weight of the person on the ladder pushing downward in the minus j hat direction. I got the wall pushing outward. This is a normal force. Remember, there's no friction on the wall. And then I've got these two forces from the ground. I got the normal force of the floor or the ground pushing up, so the ladder does not penetrate the ground, and I also have a friction force on the ground to keep it from sliding back and forth, right? So when I ask about the force from the ground, I'm really asking about this perpendicular component, the normal component, that force from the ground, and the horizontal component, that friction. So in solving for this thing, we set up forces left and right, have to add up to 0. The forces vertically have to add up to 0. And we also had to take a moment about some point. And when we did so, we found that the normal force on the ground is equal to the weight of the person on the ladder, just because those are the only two forces that are acting vertically. And then we also found that the force of friction was this expression right here. So it depended upon the weight of the person, the geometry, that is how long the ladder is, where the person is along the ladder, and the angle at which the ladder is leaning, the theta. Now this problem that we solved in this case, notice that everything was given to you symbolically. The length of the ladder was L, the weight of the person W, the angle at which the ladder is leaning, theta, and so forth. Right? I didn't give you numbers. That might be uncomfortable or unusual for you. In your statics class, you might have had numbers all the time. Well, in dynamics, I'm going to give you symbols because they're more general. They're better to work with. If you can solve your things generally in terms of these symbols, then you can substitute any specific numbers you want, and you can look at whole families of solutions if you want to. And that's what we're going to do now. We're going to look at whole families of solutions, and we're going to do so in a computational environment called VPython. If you haven't done any programming yet, we're going to try to keep this very simple. All right, so the first thing I want you to do is to go to your web browser, and I want you to paste in that URL I gave you for this very first assignment. So I'm pasting mine in right now, and when I do, it should take me to this website called trinket.io, and in particular it should take you to a trinket that I've set up for you that looks like this. Actually, I guess it's a partial trinket. A trinket is just a program. It's a set of instructions that'll execute, and we're going to be writing our code in a language called VPython. VPython is a variant of Python, which is a very powerful modern programming language. We've got a variant that allows us to do some nice graphics that we'll be doing throughout the semester. So if you've never written Python code or any computer program, I don't think this is going to be hard for you. This should be pretty easy, at least to begin with. So in Python programming language, whenever you see this pound sign right here, that means whatever follows it's a comment, and it's going to be ignored. So here's where I'm just writing a comment. It says we're going to write a program to plot the solution to a statics problem. It's the statics problem with the ladder that I told you about. The next thing on here is a print statement. So when we run this code, in fact, you can just run the code that's right there on the right hand side here. It says written by question mark, question mark, question mark. So what's happening is it's taking this stuff inside the quotation marks and it's printing it on the screen. Yeah, it's kind of cute. So if you want, you can put your own name here, if you will. I'll put my dog's name in there, Stanley. And when I click run, it says written by Stanley. Yeah, so go ahead and try that yourself. Make sure yours is working just like mine is. Alright, so as I'm doing this, I'm hoping you're doing it right along with me, right? You're not just listening to me passively. You're actually doing this with me. So at any time you can pause this video and try something out for yourself, right? So I'm hoping right now you've already tried changing this line right here so that it says your name in here instead of just Stanley, unless you like my dog, and work with me. All right, so let's continue along this program. Again, the next two lines have these pound signs there, so it's commenting stuff out. So these are actual lines of code that I'm commenting right now. So right now I'm just telling it to ignore those lines, and we'll uncomment those later so they'll actually become part of our program. I got some stuff going on here. So I've got a variable I'm calling theta begin. I'm setting that to be 10. Theta end, I'm setting that to be 80. D theta, I'm setting that to be 5. Okay, these are just variables. So these are things within the program that hold numbers. And so I'm putting the number 10 in a variable with the name theta begin. I'm putting the number 80.0 in a variable called theta end, and so forth. Right? I'm doing more stuff down here. I've got L, D, and W. Right? These symbols or these names probably sound familiar. In fact, I hope they do, because remember, these are variables in our statics problem right here. Right? L is the length of the ladder. D is the distance the person is up the ladder, the person of weight W, that is, and the ladder's leaning at an angle theta. Right? So these variables have significance in our problem. And right now I'm giving them numbers, right? When we solved the problem originally, they were just letters, they were symbols. And now we're going to choose numbers for these things. All right, so for example, I have this variable W, so it's 190, and my comment says that's in pounds, LBS. So if I wanted to, right here, I can write print W. It's an uppercase W, so be careful. These languages are case sensitive, right? So an uppercase W would be different from a lowercase w. And we'll just write that in there. We'll click the forward button, and note it says written by Stanley, and then it says 190 because 190 is the number that was inside the variable W. Now I want you to notice that when we printed this out, I didn't have any quote marks. Where my statement originally up here, I did have quote marks, right? It says written by Stanley, and whatever was in the quote marks was what was printed on the screen. If I put quote marks on this one, let's just try it real quick. Put quote marks on this one and run it. It's going to print, there it is, the letter W, right? I don't want to print the letter W. What I want to do is I want to print the contents in a variable called W. So if you actually put stuff in quote marks, it actually prints literally what's inside those quote marks. If you print a W or any other letter or any other symbol, it could be theta, right? Theta, think about what that's going to be. I've got a variable called theta, and I've got a variable called theta begin. Theta begin got 10, right? That's what was put in there. And then inside theta, I put whatever was inside theta begin. So theta begin has the number 10, and so I'm going to take that number 10 and put it in theta as well. That's what this line here says. Let's just try it out. So I'm expecting this to say 10, and it is, right? So this happens because, again, I don't have quote marks here. I'm actually printing out the contents of that variable, in this case, theta. All right, so let's get going now. So let me get rid of this print theta here. What I'd like to do is is have my program do some important arithmetic for me. So remember what I was after in my statics program was the force from the ground. The force had two components, a normal piece and a friction piece. The normal piece was easy. I called that NG, by the way. I'll call it N underscore G. And what was that? That was just W. That one's the easy one. Then I had the friction force at the ground. And that was a little more involved. It had a W. In fact, let's go look at that expression if we can. It had a W times a D cosine theta in the numerator. And it had an L sine theta in the denominator. So let's go put that into our program. So I got a W times, what was that, D? So multiplication in Python, as in most computing languages, is the asterisk symbol. So W times D times cosine of the angle theta. And then we're going to divide it by, a bunch of stuff. So let me put some brackets in there. And we're dividing by L times sine theta, if I remember correctly. Yeah, so what I'd like to do is print out both of these things now. So I'll print, and check out this. I'll try to make it pretty. Hopefully I'll do it right. So I'm going to say N underscore G equals, so that's in the quotation marks. And then I'm going to say plus, and then I say N underscore G, and then I'll say plus, and then I'll put a space there, and I'll say F underscore G equals, go outside the quotation marks, plus F underscore G. Check that out. Let's see if it runs. I'm going to cross my fingers and hope I got the syntax right. All right, let's click this. And holy cow, that looks cool. So it actually prints out the letters. So N underscore G. So that was inside the quotation marks. And then I add to that the NG, which is 190 pounds, right? That was the weight. That's exactly what we expected. Right? And then we got FG is, here it is, FG. I got a space, so there's a space after the 190 pounds. Maybe I should put a semicolon there instead. That'd probably be a little better. Where is it? So I thought I pressed the semicolon. There it is. Semicolon, maybe an extra little space right there. Let's run that again. Yeah, I like that better. So semicolon, a couple spaces, then FG, and then I got the whatever this calculated out for FG. Yeah, isn't that cool? Now I should state really quickly, if any of you are trying to also learn the Python programming language, remember VPython or Glowscript is a variant of Python. Python won't actually like this very much. VPython's a little more forgiving, so you'll have to look up how you would do this in Python. It's a little bit just slightly different. But nonetheless, for us, this is working actually beautiful. This is a really nice way a pretty way to print out your code. Yeah. There's just one problem. In fact, try this. If you haven't tried this yet, pause the video right now and try it out yourself. Put this code in there and also print it out. So if you've gotten this, if you actually tried on your own calculator to try to calculate these numbers, you probably notice you get something a little bit different, right? Ooh, what's the difference? Let me just try something for you. Let's print out right down here. I'll say print. Let's take the sine of 90, meaning 90 degrees, I'm thinking. And let's print that out. Ooh. So what are you expecting for the sine of 90 degrees? Right? Sine of 90 degrees should be 1, right? But this is saying that the sine of 90 is 0.893997. So what gives? Pause and think about that for a while. Why is that answer off? All right, the reason why we're having a problem here is because whenever you write a sine or a cosine or a tangent or any of these trigonometric functions, it's expecting the argument to be in terms of radians, not degrees, right? So 90 degrees would be pi over 2, right? So if instead of 90 I write pi divided by 2, try this out. Yeah, there's the one I expect, right? So whenever we have a sine or a cosine, tangent, well, all those trigonometric functions, they need to be in radians, not in degrees. So that's a little tricky. So maybe what I should do in here is notice that I have theta for both my cosine and my sine. That's totally wrong. So maybe I should, in here, I'll call it theta rad. Theta rad will be, so theta in radians will be theta. How do I convert degrees to radians? What you do is you multiply by pi and you divide by 180, right? So there's pi radians in 180 degrees. And then when we take a sine or a cosine, we'll be taking the radian angle rather than the angle in degrees. So we're taking sine and cosine of theta rad. Like so. Now I'm hopefully going to get an answer that I like better. And now the friction is 732 pounds. Holy cow. That's a lot bigger. It sounds ridiculous, but we're at an angle of 10 degrees if I remember correctly. Yeah, that's about what you expect actually. Yeah. Try it in your own calculator with the degrees. Right, this is what you should be getting. All right, so how are we doing? Hopefully you're doing the exact same steps I am and doing this, being an active participant in this lesson rather than just passively watching. All right, so let's keep going. So I have a way of computing or calculating that normal force and that friction force for a very specific set of parameters, right? That length, this distance, this weight, and the theta equals 10 degrees, right? Which is something else in terms of radians. So what I'd like to do now, and you might guess it from how I've defined up here, what I'd like to do is I'd like to plot these, or I'd like to generate the solution for the normal force and the friction force over a wide range of the lean angles theta. Yeah? So here's what I'm going to do. So here we have theta begin, right? Theta, I'm setting equal to theta begin. And what I'm going to do is I'm going to construct a loop. So I can loop through a whole bunch of different angles starting at 10 degrees, going all the way up to 80 degrees, and doing it in increments of 5 degrees. So I'll start off at 10, then I'll go to 15, then 20, 25, 30, 35, 40, all the way up to 80 degrees. That's what I'd like to do. So watch how I do this. I'm going to construct what's called a while loop. So I'll say while, and I'm going to open up a parentheses here. I'm going to say while the theta is less than or equal to theta end. Okay? And I'm going to put a colon sign after this. Okay? It's really important to put the colon here. Notice when I put the colon there and hit enter, it's going to indent a little bit for me. That's very important. Don't get rid of the indent right now. And what I want to do is I want to print the value of theta. Okay, so and then I'm going to do this. Just bear with me. Just type in the same thing I'm doing right now. Then I'm going to say theta is equal to theta plus d theta. Yeah? Do you understand what's going on here? Actually, let's just run it. Yeah? Let's stick with that. Let's run it. So I'm going to hit run. Here it goes. It's doing its thing. And oh, look at that. It scrolled up stuff out of the top. So at the top it says written by Stanley. And look what happens. So I'm right here. Theta is going to equal to theta begin. So theta is 10, right? So then it goes into while theta is less than theta end. So theta is 10, theta end is 80, so theta is less than, so theta the 10 is less than theta end, which is 80. So it's going to go inside here, and it's going to print the value of theta, so it prints it. Yeah, and then what happens? It says theta equals theta plus d theta. Well, when I say equals here in a program, it's not the usual equal sign that we have in mathematics. This means to make an assignment. Okay, so let's look on the right hand side. On the right hand side, I got theta, and that's 10. And I'm going to add d theta to it. So 10 plus 5 would be 15. And I'm going to take that 15 and I'm going to assign that number to theta, right? That's what we did before. When I said L is 25, I took that number 25 and I assigned it to L, right? So in this computer programming, the equal sign is an assignment. Here I'm assigning a new number, 15, to the variable theta. So now theta becomes 15. And 15 is still less than 80, so it prints out the 15. And then it adds 5 to the 15 to get 20. It puts a 20 inside theta. And then, and since 20 is still less than 80, or still less than or equal to 80, then it prints out the 20. And then it keeps on going. And it does 25, and it does 30, and it does 35, 40, 45, 50, 55, 60, 65, 70, 75. And then it gets to 80, so 75, when I have 75 here, I add 5 to it, I get 80. And it says 80 is less than or equal to 80, so it still prints out the theta. Yeah, and that's why we see the 80. And then it adds 5 to the 80 and gets 85, and it says, is theta less than or equal to theta end? And it says no, right? So what it does is it breaks out of the loop and does all this stuff down here. It says theta rad and does this previous stuff right here. And now this is the FG for, actually this is 85. This should be for 85 degrees. Because remember, theta was 85 degrees by the time we ended this loop. You can check that yourself. All right, so there is the program, right? But what we're doing is we're seeing this thing run through that loop. Okay, right now all it's doing is it's printing out the theta. And what we'd like to do next is have it do this entire calculation for each one of these values of theta. Okay, so the way we do that is we take all this stuff out here and we put it inside of our loop. And when I say inside the loop, that's the stuff that gets executed each time it runs through this check. And the stuff that gets executed with this while statement is the stuff that's indented. So what I'm going to do is I'm going to take this stuff right here. In fact, I'll take all of that. I'm going to copy it, Control C, and I'm going to paste it right here. See if it goes in nicely. Okay, it went kind of nicely. The first line went in nicely. That's indented. I'm going to have to indent these other ones too in order for them to be part of my loop. All right, and let's add a little bit more to my print statement. Let's say, let's go theta equal to, and I'll say plus theta plus, inside here I'll put the semicolon space space. Yeah, how's that look? Looks promising to me, I think. I'm looking at it. I'm looking for problems. Since I've already pasted this stuff in there, let me get rid of that. And let's try it. Let's try it. I scrolled everything up. I gotta come back down. Boom. There it goes. Look at that. That's cool. So at theta 10 degrees, my normal force is 190. My friction force is 732.72. Right? Normal force 9. So this is the normal force. Actually, the normal force is the same each time. But you can see how the friction force is changing, right, for each one of those thetas. And we can actually calculate it. Isn't that awesome? We can do that whole run. And how long did it take to do that run? With Glowscript, it took a couple seconds to do that run. And other programming languages would take a very small fraction of a second. All right, so this is kind of cool. I'm getting a bigger picture of what's happening. So that friction force starts off huge, and for 80 degrees it's actually pretty small, 22 pounds. Doesn't take a whole lot at that point. It's a small fraction of the 190 pounds of the weight. All right, cool. All right, there's one more thing we need to do. One more really cool thing. So what I've done now is print out a whole list of these numbers. These numbers are okay to look at, I guess, but they'd make more sense to us, at least for us visual people, if we can graph them, put them on a plot. And that's exactly what we're going to do next. All right, so to make this plot, the first thing we're going to do is we're going to go up to the top here and we're going to uncomment this line up here. It says my graph equals graph, and perhaps you can sort of figure out some of what's going on here. We're going to create a graph. It's going to put a title in here called my plot, and it's going to put on the horizontal axis, the x-axis, this thing that says theta in degrees. So I want to plot theta in degrees on the x-axis. I want to put the forces, both forces, on the right axis. So the first plot, the actual curve, it's called G curve. Actually, let's give it a better name. Let's call it the NG curve. This is the normal force, right? We'll do the normal force in blue, and actually let's copy this. So I'll go to Control C to copy, Control V to paste, and I'll call this FG curve for the other one. FG curve, and we'll make that one green. What do you think? Yeah? So let's just see what we got. All right, so we've defined two curves that are going to go on my plot, and it's really easy to do this thing. So right here, after I calculate those two things, I'll call it NG curve. Now I got to be careful again with the upper and lower case. It has to match exactly. These languages are case sensitive, so in mine I made the letters N and G uppercase and the rest of the name lowercase. So please be careful with that. And to actually give it data points to plot, it's really simple. You say dot, and you say plot. I think it's plot. That'll be my guess. And I'm going to put theta in there. This is the angle in degrees, right? I want to plot in degrees. And then I want to put the result in there, N underscore G. So I'm giving that curve a data point. And again, this is inside the loop, so it's going to do it for every value of theta that we loop through. And then I'm going to say FG curve dot plot. We'll call it theta and FG. Like so. And again, I'm crossing my fingers here. It's just so easy to make a mistake. So don't get frustrated if you do it. You just have to go back and figure out what you did wrong. And that is, by the way, when you write code, it's best to write a few lines of code at a time. Right? Just run a few lines of code, check it, see if it's doing the thing that you expect it to do, and then if it is, you move on. Right? Little bits of code at once, at any one time. So I think I'm ready to try this thing. Now I'm going to click the button, and oh, look at that. That's beautiful. Let me move this over. Yes? Cool. So it has this table that we printed out down here at the bottom. There's all those numbers again. But the new thing are these curves. Isn't that beautiful? So the blue curve is what? That was the normal force, right? And the green curve was the friction force. You know, it would be really cool if we labeled these curves. Check this out. So here's what I'm going to do. I'm going to label these things. So let's go back over here. So the blue curve, this was the normal force, right? So I'm going to say label equals, I'm going to say normal, right? And I'll put a label on this one. And I'll call this friction. Those are nice labels, right? Notice also on my graph I've got a nice label for the x-axis. That's theta in degrees. On my vertical axis, I should probably label that thing too. So the horizontal axis was called tidal, x-tidal. Let's do the same thing for the vertical. I'll call that y-tidal. So y-t-i-t-l-e equals, and I'll say force. I'll put that in LBS. Yes, I'm liking this. All right, check it out. I can run it. Boom. All right, so notice this. Check this out. It labeled the vertical axis, which is cool. And also over here, look, it gave us a legend. So it tells me the blue is normal and the green's friction. Isn't that sweet? That's what happens when we put the labels on. Very nice. Notice also that it put these little markers in here. Oh, look at this. If I drag my mouse over the curve, I'm not pushing the mouse button at all. I'm just sort of scrolling this little target over the curve. It actually gives me the numbers, right? Oh, isn't that nice? In fact, you can see it's 190 pounds for that normal force. That's nice. I like that. So why don't we, since the numbers are already on the graph, we can get them. There's no use in printing them out down here, right? So let's get rid of this print statement. I'm just trying to clean this thing up, right? Let's get rid of this print statement. I don't need the print statement. I don't need to print all those numbers out. To get rid of it, I can erase the thing completely. Or maybe I just want to hide it from the computer program in case I want to bring it back later. To hide it, again, you essentially comment it out. So you put that little pound sign there. And notice I still have this print statement lingering on from before. I don't need that one anymore. All right, let's run this again. Even cleaner. I love it. I love it. And it says written by Stanley. Sweet. My dog will be so proud. All right, so we're looking at that every 5 degrees. You know, it was so quick to count that. You know, you don't have to do 5. We can do 1 if we want. Let's do 1. 1. Boom. Woo, you can see the mark. You can see it more. It's every 1 degree. So you see a lot more markers here, right? So for every point that we're calculating, it puts one of these little dots on there. That's the marker. So if you want, you can leave those markers off if you want. You can say, instead of saying true, you can say false. It's important to make false start with a capital letter, capital F. Yeah, let's try that. Ah, nice smooth curves. Look at that. That's beautiful. Yeah? All right. I like it. So in this, you learn how to program in Python. Congratulations. You learn how to create these cool graphs. You learn how to construct for loops. You learn how to do some arithmetic manipulations with these variables, right? Congratulations. Pat yourself on the back. We're done. Over and out.